Welcome to the Energy Overview section. In this section, you'll see a blizzard of facts, seemingly unconnected facts, all about the current energy system, about where energy comes from and where it goes, how it varies within countries, how it varies between countries, a little bit of the history of how those flows have changed over time, something about the prices and costs of energy. All of this will give you some snapshot of the way the world works today. That helps you understand the energy system as it is now and also understand how it might be changed. So here's how this section is organized. First, we need to talk about units and conversions. This may seem a little dry, but you have to understand the language before you know how to understand the facts. Then we'll talk about energy flows today, talking about the flow of energy from where it enters the economy to where it provides some useful service, like the computer and illumination that allows you to see this video. Then we'll talk about the global trade in energy, about historical trends, and about prices and the fact that energy is, in some kind of fundamental way, a commodity. Now, some useful definitions that help us talk about energy as it flows from where it enters the economy to where it does some useful work and provides some goods and services that we want. There are four common terms. First, primary energy. Second, final energy. Third, useful energy. And then energy services. Let me take a moment to define these and give you a few examples. So, primary energy is energy the moment the energy enters the economy. So this would be oil or gas, where the oil and gas actually flow out of the shaft coming out of the ground. Or coal at the coal face, where the digger digs it. Or wind power, where the torque is applied to the generator. Or electricity in a solar photovoltaic, where the electricity comes out of that first photovoltaic. That's primary energy, where the energy begins to have a price and enters the economy. Final energy is energy in the form to which it is sold to some entity that wants to buy it. So that might, for example, be electricity or processed fuels. So, for example, crude oil is not final energy, but gasoline or kerosene for a jet aircraft is final energy. Then there's useful energy. Useful energy is the energy in the form that is finally used to provide some good or service. So, for example, this might be the motive power coming out of an electric motor in an electric car, or it might be the energy flowing into a computer. Then there's energy services. Energy services are goods and services that humans actually want, for which energy is one of the necessary ingredients. In some cases, energy is a pretty important part. So, for example, when you think about home heating or illumination, it's clear that energy is a key part of that service. But on the other hand, you can also think about garments, the clothes I'm wearing, as an energy service in the sense that there was energy as an input, although in that case energy is a relatively small part of the total cost of the service, and it doesn't determine much about the garment. So let's give some specific examples. Oil that's in the ground, ready to be economically extracted, is a reserve. Then you drill the oil and extract it. The oil that comes out is primary energy. Then it flows into a refinery, which converts it to the final sold products, like, say, gasoline. Gasoline is a final energy. That gasoline would go perhaps into a car, into an internal combustion engine in a car, and that internal combustion engine produces torque on a drive shaft, and that drive shaft is the useful energy. And then there's the actual transportation, the fact that the car takes you from A to B, and that's an energy service. Now we can notice a key distinction. Primary energy, final energy, and useful energy are all measured in physical units of energy. So they're all measured in joules or kilowatt hours, physical units. Energy services are not measured in physical units. So an example of energy service would be the passenger miles or kilometers traveled in a vehicle. But that's not in energy units, and there's lots of different things that goes into determining that. An energy service might also be the amount of computation you get or the amount of illumination you get, but those do not have energy units. There's an important consequence of this shift in units. When you think about the chain from primary energy through final energy to useful energy, you can define an efficiency. And that efficiency has the natural physical interpretation. It's a dimensionless number, and it has to be less than 1. So if you think, for example, about the efficiency that goes from coal being extracted to a drive shaft of a final electric car, you can think about the efficiency all the way through that process, and you know for sure that the efficiency is less than 1, and you know that the efficiency can be calculated by multiplying a bunch of individual efficiencies for each step. The same is not true for energy services. Energy services are not measured in energy units. And strictly speaking, you shouldn't talk about efficiency when you talk about energy services. You should talk about efficacy, where efficacy is the ratio of the energy in to whatever the service is that you're getting out, which could be the amount of computation, or it could be the distance that you travel in some vehicle. So let's take the example of personal vehicles, of cars. So it's actually common in everyday speech to talk about the efficiency of a car. Well, what we mean is the liters per 100 kilometers or miles per gallon of that car. But that, when you think about it carefully, is not actually correct. And here's why. For an efficiency, the units in and units out are the same, and you can divide them and get a dimensionless number called efficiency, whose maximum value is 1. But there's no way to think about that for a car traveling on level ground. So think about the inherent energy cost that it takes to go, say, 100 kilometers in a car on level ground. If you think back to Physics 101, you're not going up or down. So there's no inherent energy use to do that. Sure, there's energy use in an actual car overcoming friction, but that itself is a design feature and depends on how fast you're going. So when you talk about liters per 100 kilometers, what you're really talking about is the efficacy. And it matters because there's no upper bound. And you can't know for sure how much more efficacy you can get. And unlike something like a motor where you can talk about efficiency, and that's in a sense the only quantity you care about when you're talking about energy in to energy out, for a car, there's a whole range of properties we care about, from acceleration to safety to interior volume, and all of those trade off in complicated ways with energy use. Because the final product that a car gives us is not just measured in joules, it's measured in a whole complex host of things, from its ability to go fast, to its ability to go safely, to, let's be honest, its ability to impress our friends. And all of those things together cannot be boiled down to a single number, and talking about the energy efficiency of a car, therefore, is in some deep way a misnomer. And that, as you see, will matter when we start to think about energy efficiency throughout the economy.